So welcome everybody to lecture number 3, which I've entitled How the Lighthouse Shines. And what I'm going to try to explain today is how we believe that radio emission comes out of the pulsar. So far in the first lecture I sort of introduced some broad themes, and then you'll recall last week I spent a lot of time trying to describe to you how it is we get a neutron star, how it is we get a pulsar. Now we've got a pulsar, how is it that it manages to make the radiation that we see? So that's what I hope to explain today. Come on. Where's my guy? There we go. Okay, so this is where we've been, where we are today, and next week we're going to have what I think will be an interesting one, how pulsars meet Einstein. So I only wrote this slide this morning. This particular slide, the lecture was already prepared, but I feel like I'm going to be introducing quite a lot of different stuff at maybe a higher rate than normal. I try to be gradual. This week I feel like there's no real way to be gradual. I have to kind of add pieces of the puzzle. So I thought I would sort of show you all the pieces of the puzzle first, and then we're going to build a picture together. So what we're going to start off talking about is the difference between thermal and non-thermal radiation. And then I'm going to talk about something called coherent emission, which is special for the radio emission from pulsars. This is sort of a particular feature of the radio emission that is coherent. And then I'm going to explain how the spinning magnetic field from a pulsar creates an accelerating electric field. And this accelerating electric field accelerates charges, and these charges, which are accelerated, make the radio beam. And these accelerated charges, after they leave the pole, they also fill up a cloud of particles around the neutron star, and that's called the pulsar magnetosphere. And the other emission that we see, the optical emission, the X-ray emission, and the gamma ray emission, most of that comes from the pulsar magnetosphere. But this cloud of particles that's in the pulsar magnetosphere, they also leak out of the magnetosphere. And they leak out into a region surrounding the pulsar, and that's called the pulsar nebula, and they look pretty spectacular. And after I kind of describe how the pulsar nebula, then I'm going to hopefully tell you where the optical X-ray and gamma ray emission comes from. All right, so let's get a move on. Oh yeah. So one of the questions somebody asked last week was, how is it that blue is hotter than red? And I gave an answer, and I thought about it afterwards. And one point I didn't make is that when you look at the spectrum, it's also just the energy of the photons. That's a key thing that I didn't say, is that the energy of the photons depends on their frequency. And so higher frequency photons have more energy than lower frequency photons. And the blue radiation, the ultraviolet radiation, is higher frequency than the red. So that's why it's hotter. But I didn't say that. But anyway, this is what we call our electromagnetic spectrum. And the thermal radiation that we're sort of used to happens mostly in this regime right here. So hot stuff makes infrared and visible light. Ultraviolet doesn't make visible few X-rays. But it doesn't really make gamma rays. It does make thermal radiation also extends into the radio and microwave, but that's not typically how we make radio and microwave photons. Typically we use non-thermal processes to make radio and to make microwaves, and also to make high energy X-rays and gamma rays. Now the non-thermal stuff happens in this gap as well. This is not like a special zone. Like in here non-thermal works as well, but just this is our familiar experience that we are familiar with, is that thermal happens in this region and non-thermal happens in these other regions. And for people who've had a chance maybe to read the flyer, what I try to explain in the flyer is that the thermal radiation comes from the kinetic motion of the atoms. So the positively charged nuclei and the electrons are sort of vibrating around because they're warm, and this wiggling emits photons, and that's thermal radiation. Non-thermal radiation, which is what comes from pulsars, comes from particle acceleration. And there's other ways to get non-thermal radiation, such as particle collisions, nuclear decay, And this strong magnetic and strong electric fields, these all play a part in giving you your particle acceleration that's available. And so, just to show you what thermal radiation looks like, as an example, this is a thermal imaging camera. So this was at nighttime when our eyes do not pick up the photons at night, they're not sensitive to that. But we have detectors that are sensitive to that. And so you can see the hot bat, and he's emitting thermal radiation. Above him, you can see his other bat friends, but also the cloud in the sky, it's also hot and making thermal radiation. And the emission that we see from the sun, that's also thermal radiation. And if you have a camera that's sensitive to thermal radiation and it looks at the Milky Way, then that's how it would look. And most of the stuff that's in here is warm dust and starlight. So non-thermal radiation is the stuff that we talked about last week, which is when you, an example of non-thermal radiation is what we talked about last week, where if you bind the lighter elements together and make heavier elements, you get photon energy out. And this isn't to do with vibrational motion. This is to do with the fact that the lower, the combined total mass of the lower end of the lighter elements is lighter than the total mass of when they combine. And so that mass difference makes some energy in the form of E equals mc squared. And so these photons that come out here, that come out at the center of the sun, they are non-thermal. Later on, everything heats up, and it's the vibrational motion in these zones here that make the light that we see. We don't actually see the photons from the core. And so, as I said, how do you make, or as I tried to introduce, how do you make non-thermal radiation? So, let's have a little example. If you take two metal plates and you attach a nice little battery, then what will happen is charge is going to build up on the plate attached to one of the connecting points, and an opposite charge will build up on the other. And this creates an electric field between the two plates. And if you plop a charged particle in there, it's going to feel that electric field and it will be accelerated. And so, which way will it move? Everybody knows that the positive wants to leave its positive buddies and escape to the negative guys, and so it'll move in this way. And this is an example of particle acceleration. And if you had a situation like this, which everybody used to have in their TV set, non-thermal radiation comes out. So it's just charged particles that are accelerated emit non-thermal radiation. And like I said, everybody used to have a particle accelerator in their house. Maybe you turfed them out, but you used to have them. Now, I just put this slide in just for a sense of completeness. So I just told you the story that there's non-thermal radiation in the center of the sun, holding away, pushing away from the gravitational force. And then the outer layers of the sun, that then kind of thermalizes that, and the atoms wobble and they make the thermal energy that we see. Outside in the corona, where there's a lot of magnetic field lines and so on, non-thermal energy is created in the corona in the form of, this is an image of the X-rays from the corona of our sun, and the X-rays that are created out here are created through non-thermal processes. Now, this slide is one of those places where I feel like I'm just dumping stuff on you that I didn't properly have a way to build up to, but this is the way we got to do it. So, you know, when I say, oh, thermal emission comes from the wiggling of, hot atoms, but non-thermal emission, where does that come from? What are these processes? So, one of the most important processes for making non-thermal emission is called synchrotron emission. And this happens when you have an electric field and a magnetic field, and the particle is accelerated by the electric field, but as it's accelerated, it spirals around the magnetic field and it sort of shoots out a cone of photons. And that's called synchrotron emission, and that's an example of non-thermal emission. If you have incredibly strong magnetic fields, like the ones that are found in pulsars, we find that the spiraling doesn't happen, and instead the particle just moves along the field. And so, because it's moving along the field, the beam of the radiation comes out in a different direction. Whereas over here in the synchrotron case, as it's moving along the field, it's also spiraling, and so the emission kind of comes out this way as he's moving along the field. Whereas if you're in a very strong magnetic field and you're emitting curvature radiation, you're shooting your photons out straight ahead. But essentially, nothing else. There's no real difference between synchrotron emission and curvature radiation. Just the strength of the field is different and the direction of the beam is different. Now, this is a process that isn't necessarily non-thermal emission, but I just wanted to make sure everybody was familiar with this process. That if you have a photon and it bumps into another photon, and these photons are of sufficient energy, you can create a pair of electron-positrons. So positron is just a positively charged electron. And so if these guys have enough energy, then they can make these guys. And everything is conserved. The energy that was in these photons is converted to the mass and energy that's in these electrons. And beforehand, there was no charge. There was no net charge. And afterwards, there's no net charge because the positive cancels the minus. So nothing is violated here, and this process happens. But it also happens that a single photon, if it's in a strong magnetic field, can also do this process. So that's an important process for pulsars, that an energetic photon can interact with a magnetic field and make charges. All right. Now, I've just told you how it is that if you accelerate charges, they emit these photons through either synchrotron emission or curvature processes. And the energy that is radiated is proportional to the charge squared. So if you say the charge on the electron is QE, then the energy from one individual electron is proportional to QE squared. And so if we have three photons, if we have three electrons and they're all radiating and they're in this sort of configuration, they're hanging out, moving along the magnetic field and radiating their non-thermal photons, then the energy that comes out is proportional to 3 times the charge of the electron squared. And this is called incoherent emission. And the reason I introduce incoherent emission is because I want to talk about coherent emission, and I have to give you some contrast. Coherent emission, okay, so that's a little cartoon of the photons coming out of the particles, of the charged particles. Now, incoherent happens if the particles are closer together and they're moving at exactly the same speed. If you set up this situation where you manage to get your charges to be close enough and to move at the same speed, then you get coherence. And coherence is a property that instead of it being, it's proportional to the charge squared, but we can consider this to be these three charges to sort of be one charge. And so instead of it being 3, it's 9. And so coherent emission is brighter. If you're able to get your particles to radiate in a way that's coherently, you end up getting more radiation out. Your radiation process is more efficient. And so this is what's happening to the radio emission from pulsars. The radio emission from pulsars is coherent. Now I know I'm just sort of talking abstractly now, and hopefully this will get tied in later to the diagrams I'm going to show. But an important message, and a message that people don't pay enough attention to, I feel, in the pulsar community, is that the radiation from the radio is coherent. That means that it doesn't come from an individual electron, but it comes from a bunch of electrons that are all together as a group. Okay. So this is a picture of a handheld radio. And a very, very simple sort of explanation of how a radio works, because you'll have some circuit in here. There's a bunch of amplifiers and all the rest of that, but for simple purposes, it's just a circuit with a little battery. And the current in the wire, which is just a bunch of charges, get, shut up the antenna and down again, and radio comes out. That's how your cell phone works. That's how a two-way radio works, pretty much. Oh, we're here already. Okay. what I'm going to try and tell you now is how a pulsar gives us this fellow, which is the accelerating potential, the electric field. How do we get that from a pulsar? So this is a little movie made by a researcher at Goddard Space Flight Center, Andrei Timokhin. He's a theorist and he works on pulsar magnetospheres, and he made this little movie and I stole it. And I'm going to show it to you guys. And I want to just lower the screen down a little bit. Or how do I work this stuff out? Okay. So what he's going to do is he's going to take this magnetic ball, which he found somewhere on eBay, I believe, and he's going to attach it to the nozzle of a drill, and he's going to spin it around. And then he's going to demonstrate that the spinning ball makes a current. All right, let's do it. So first he's going to show that when it's not spinning, you don't get anything. I wanted to do this live for you guys, but I couldn't find the appropriate magnetic ball. So you can see that there's no current being registered on the current meter. And there we have some current. Now, what he's going to do is he's moving the electrodes to different points along the ball. So he's sort of, I'm going to show it again, but he's sort of at the north pole and the equator. Or well, now he's at this, if you consider it to be the sort of the left pole on the equator, and then he moves it over to the right pole on the equator, and you'll see that the current changes sign. Then, do people see that? All right, good job on there.
And what voltage was the maximum that you obtained?
Oh, I don't know. I don't know.
It looked like 17 volts.
So this was reading at microamps, I guess. So this is a current measurement. Okay. So I hope if Andre can sit down with a little magnet and a drill and make some current happen in this tabletop pulsar example, and after I told you the last 2 weeks about how strong the magnetic fields are from these pulsars and how fast they're spinning, I guess you will believe that the electric fields you can make are enormous. And so the spinning, the rotating magnetic dipole generates a voltage which can drive a current, which can be, and so yeah, so one thing Emil told me to sort of give a sense of scale. So I talk about how pulsars are incredibly strong, 10 to the 15 Gauss. Well, what does that mean? What does that mean? So just as an example, if you have a compass on the surface of the Earth, that compass needle reacts to the Earth's magnetic field at this distance, which is half a Gauss. If you manage to burrow into the Earth's core, you would feel about 25 Gauss. Your fridge magnet is about 50 Gauss, and if you have to go get an MRI, you're going to sit in 50,000 Gauss. But this is nothing compared to 12 zeros at the end. Like, so just to give you, I should, this is probably one of the slides I should have shown on the first week, but I forgot. All right, so now this is our cartoon of the pole of the neutron star. So this is, and so yeah, I realized when I made the slide that people might think that this is like north and south. It's nothing to do with north-south. It's just NS stands for neutron star. And we have the magnetic field lines coming out. So they're coming out at this sort of angle. So in this diagram here, the magnetic axis is not aligned with the rotation axis, which is going straight up. And so, by the same principle that Andre showed you on the video, this spinning magnetic field is going to make our strong electric field. And when you think electric field, I want you to think about the two plates I showed you earlier on. What's going to happen is that any electron that is in this region here, is going to see this electric field. It's going to move outwards because the field is pushing it, and as it moves along the magnetic field, it's going to emit those non-thermal photons. Now, I told you that if you're a photon and you live in a very strong magnetic field, one thing that can happen to you is you can bump up against a magnetic field and pop out a pair of electrons and a positrons. And so that's an unlucky photon that might be making it to the Joshua Bells of the world who are out here, never makes it. It bangs into the magnetic field and it makes a pair. And this guy is, say, he's negatively charged and this guy's positively charged. And so they're going to move in opposite directions, because if you have sort of a standing positive field on one plate on one side and a negative plate on the other side, and you put two charges of different sign in, they're going to move in opposite directions. And so what happens is that the electrons come out this way, the positrons go down this way. And this sort of shorts out the potential. So if you have a battery and you just put like a wire between the two antennas, or the two electrodes, current will flow and it will short it out. In order to not short out, you need to have a load, like a resistor or a light bulb or something to sort of force the current through. If there's nothing to force the current through, then the current just goes unimpeded. It doesn't have any resistance and it shorts out the battery. So what happens is there was a big field. The particles got created. The particles kind of see the field and they basically race to their opposite directions. And this moving of current shorts out the field. But the moment the field gets shorted out, it starts to grow back again. And it starts happening again. The electrons get accelerated, and they make another cascade. And so we get a spasmodic oscillating current. That is that the voltage starts, and then the electrons get accelerated. The accelerated electrons make photons. The photons bang into the magnetic field, make more electrons, and then these electrons move in opposite directions, short out the voltage. Voltage is gone, cascade is over, and then it builds up again. So this makes sort of the particles that come outwards come out in these waves. Now, there we go. Now, because these outward waves of particles, these bunches of particles that are coming out, because they're coming out and they're coming into a region, so they started off in a region near the pole where the magnetic field lines are all collinear, but as they move outwards into higher altitudes, the magnetic field lines start to diverge. So you remember my story about coherence. If you're going to have coherent emission, you've got to have everybody together, all moving in the same direction with the same velocity. And so, this is my story about coherence. Don't forget slide 22. And so it means that the only place you can maintain coherence from these separate bunches as they move outwards is the ones that are coming out right on the magnetic axis, where the magnetic field lines are mostly collinear. Once you kind of spread away from that region, the magnetic field lines bend, and you can't satisfy the coherence condition. And so these bunches of particles that are coming out, they radiate our radio beam. And this is why on week 1, when I showed you this picture, I kind of said, this is an artist's cartoon, but it's pretty much what's happening. And now I hope I've explained the reason why it's happening. Because the radio emission has to be coherent. And the only place you can get coherence like this is along the pole. And this is why the radio emission from a pulsar comes out like a lighthouse. Now let me remind you of something else you saw on week 1. This was the first guy we looked at. And somebody in the front row said, the amplitude isn't the same. You see? Why is that? Why is the amplitude not the same? And I said something like, oh yeah, that's just what happens. Never mind that. That's just something that happens inside the pulsar. So, what the reason why these guys might have like different intensities is because of instabilities in the coherence. So you can imagine that this spasmodic oscillating current, as I called it, you know, it just has sort of fluctuations inherently in it. And sometimes you get like a really nice bunch of coherence, and so you'll get a nice strong pulse. And other times the coherence won't be quite as good, and you'll get a weak one. And so the sort of pulse-to-pulse fluctuations, and if we were to zoom in, and I will do in other weeks, we'll like actually zoom in and scrutinize the pulses themselves, you'll see the evidence of this instability. Is everyone following along? Yeah? Okay. All right. Now I'm going to talk about, so I've told you about how the radio beam comes out, and now I'm going to try and tell you about this thing which I mentioned in the handout, which is called a magnetosphere. So how do I tell you about the magnetosphere? So if you just look at my little cartoon of the pulsar spinning, and so we just look at it in successive rotations. So this is let's say we start at this point, and then after half a rotation, so after it's gone halfway around, it looks like this. A full rotation is back to where it started, and 1.5 rotations, it looks like this guy again. So one thing you can see, if you just compare point at 0 rotation to point at halfway, one thing you can see is that the North Pole, like in like positional coordinates, moves. Started out here, and then it moves over here. And the South Pole moves. The South Pole started out here, and it moves over there. So I tried to make a little shadow image behind there, so you can sort of see that the North Pole is sort of bouncing back and forth between these 2 points, and the South Pole is bouncing back and forth between these 2 points. Now imagine you're a magnetic field line, and you emerge from your North Pole, and you know what your job is to find the South Pole. And so this magnetic field line has the shortest distance to travel of the 3 that I've drawn. So he comes out, and he doesn't have very far to go. Each magnetic field line has a larger and larger distance to go between the north and south. Eventually what's going to happen is, one of these guys is going to come out. He's going to go to where he thought south was, and south has moved on. It's gone. This magnetic field line is lost. And so he sort of comes out. He sort of ends out waywardly. I'm going to show that in a minute. And so there is sort of a boundary, you can imagine, where what is the boundary that the last closed magnetic field line is? The magnetic field line that comes out and manages to find its South Pole. What is that boundary? And inside that boundary, we call that the magnetosphere. And so, while I've just said that, it's just one thing you can already learn from what we just said there is that if you have a slow rotating pulsar, you're going to have a bigger magnetosphere because the poles don't move as fast from left to right, and so it can a magnetic field line that exits will have more time to get around. So fast rotating pulsars have tighter magnetospheres, and slow rotating ones have wider. But what is it? But anyway, that's all just words. So let's have a look at some more images. So this is what I tried to explain, that eventually one of the field lines is not going to make it back to the south, and it's going to be open. So we have closed field lines and open field lines. And like good physicists like to put stuff in spheres and in jars and spherical cow and all the rest of that. So we call this cylinder is called the light cylinder. And inside the cylinder, basically things which move around with the neutron star, they can move around at the same rotational speed with the neutron star and not travel faster than light. If you travel outside the light cylinder, then you would, in order to stay in geosynchronous orbit with the pulsar as it moves around, you would have to travel faster than light. And so that creates this boundary, and we call that the light cylinder. And so the pulsar that we just that I had up there a minute ago, the one that beats it every 0.7 seconds, the radius of its light cylinder, or the radius of its magnetosphere, is 33,000 kilometers. And the record breaker, the fastest pulsar that we know, which has a period of 14 milliseconds, has a radius of only 66 kilometers. Now, this was stolen from another theorist, Anatoly Spitkovsky, and he has some interesting movies on this, well, animations on this page. And I probably should have paused this for a second. So here you can sort of see, this is the direction of the magnetic field. So there's the polar cap, the pole of one, and there's the pole of the other. And what he has plotted here is the shape of the last closed field line. So rather than in my cartoon where the field lines look like the standard sort of iron filings experiment, where you would shake iron filings down on a bar magnet and look at the shape, because of the twisting and torquing and the moving of the North Pole and the South Pole, the last closed field lines take on a different shape, and they get warped and so on. So this is how the magnetic field actually looks like inside the magnetosphere. And then any field line that emerges at a higher sort of with a larger radius won't reconnect, and it'll come out. Now the action that I was talking about at the pole, which makes our radio beam, this is happening in here, and all these particles that get created, and also the cascade particles, the particles that are moving in the opposite direction, they fill up this whole region and make what's called a magnetosphere. And so I've just drawn a green, noxious cloud. And so this cloud here is full of a co-rotating ball of plasma. It's full of electrons and positrons, and it's sort of stirred up by the magnetic field. So it's agitated by the magnetic field, and it swirls around like a giant swirling ball of electrons and positrons, and that's what's called the magnetosphere. And the magnetic field lines are like the escape trains for particles that no longer are in the magnetosphere. They escape out along the open magnetic field lines. Okay.
Yeah. But why is core rotating? Once they are emitted, why they continue the rotation? Conservation of momentum or what?
So the question is, why do they co-rotate? Why do they co-rotate? And I can't give you a satisfactory answer. I could show you a bunch of equations that people wrote down in the 60s that explain, but it's electrodynamics reasons. It's partly because that the magnetic field the moving magnetic field creates the electric field. Okay? Remember we showed the moving magnetic field creates the electric field. And the electric field and the magnetic field play a huge role in the creation of the pairs. The pairs themselves are created because the photons actually collide into the magnetic field and make the pairs. And so the magnetic field is not like kind of there as a passive observer to the cloud of electrons and positrons. It is an active ingredient, and there's sort of a feedback process that keeps all of that whole thing in balance. And that the balance of the magnetic field seeding the electric field, which seeds the photons, which makes the pairs, that whole recipe that I've described there, that is interactive. It's feeding back on itself. And it's that feedback that keeps the plasma co-rotating. But there's a bunch of equations that will explain that. So we have our co-rotating blob of electrons and positrons, and then the escapees coming out, and they fill what's called the pulsar wind. And so at the center of a pulsar wind nebula, we'll have a neutron star and a magnetosphere, and then a pulsar wind nebula, which is a big blob of escaped particles. Yeah, that's what I said. Pulsar magnetosphere in there. At the center of the pulsar magnetosphere is a neutron star, and then the escapees live. And so this is a picture of probably the most famous pulsar wing nebula. This is called the Crab Nebula. And this was formed in 1054, or at least we knew it was formed in 1054. It happened, many light years away, so a lot longer ago than that, but we learned about it at that time. And this is an awesome picture. We could just sit here and look at this. I could sit here and look at this all day. And so what's happening here, so this bright spot in the middle, that's our magnetosphere. The blue, wispy, awesome, glowy stuff, that's the wind. And just to give a sense of scale, this, what they call the inner ring, the astrophysicists call it inner ring, the distance of that from the magnetosphere is about 1 light year. And what we're looking at, I should say, is X-ray emission from the Crab Nebula, recorded by the Chandra telescope. And then I have a nice...
How big is the light cylinder?
How big is... So what did we have? The fastest guy was 66 kilometers.
So it's right in the center.
Well, but the Crab is only has a period of 33 milliseconds, so it isn't as fast as... So it's... I would say that we probably can't see the light cylinder, actually. Like, when I say that this is the magnetosphere is actually probably right deep in the center there that we can't see. We're just kind of seeing the emission in the immediate vicinity of the magnetosphere, of the light cylinder. And you can see these jets. So can you see that? It's sort of a bluish glow that comes out here. That's called a jet. And there's another one coming out the back there that you can't see so well in this nebula. So let's now look at an awesome movie made from the Chandra X-ray satellite and the Hubble Space Telescope, who observed this nebula for about a year. So I don't want you to confuse the sort of wavy stuff with the rotation stuff. Like the rotation that's happening of the pulsar is happening at a much, much faster rate than this. Like I said, these images were recorded between 2000 and 2001, November and April. So, and it's 7 images that have been. So, just to look at this now, what we see in the X-rays is sort of emission from the magnetosphere. We don't see optical. It's going to come back. These bright spots here are not actually related to the nebula. They are stars in the background. And so you can see right kind of in here where I'm pointing, we don't see any optical emission from the magnetosphere, whereas we see X-ray emission from the magnetosphere. But when people saw the Crab Nebula, actually, so astronomers have been looking at this thing in optical, particularly for about 300 years. And once the kind of astrophysics started to get sophisticated and people started to write down, what they thought was happening in these objects, they sort of figured out, like, something is wrong with the Crab Nebula because it's too bright. Why is it so bright? And so they inferred there must be an energy source. There must be some energy source we don't know about. And in the big story I told you in the first week about how we discovered pulsars and how it all fits together and all the rest of it, one point that I didn't bring up, which is a very important point, is that a pulsar, when the pulsar was, when the rotating neutron star was presented by Zwicky in the mid-1930s, but it wasn't found by Anthony Hewish and Joshua Bell till the 1960s. So in those 30 years where it actually hadn't been directly observed, people basically said there has to be one in this guy because that would explain where the Crab Nebula is getting its energy source from. They kind of knew there had to be an energy source, and theorists like Zwicky had said, oh, there's a thing called a neutron star and it has a swirling magnetic field, and so they went, okay. So one of the first targets when Joshua Bell and Anthony Hewish proposed that they found their pulsars, one of the first things their colleagues did was like, let's get on the Crab Nebula. And they found a pulsar in there, a Crab pulsar. And that was a huge victory for the idea that these pulsars, where this pulse signal that Hewish and Bell were seeing was coming from this rotating neutron star. And it also helped the association with supernova remnants. So the story that things come from supernova remnants, this was born in a supernova remnant that was witnessed by people in 1054, looked up and made little, you know, mentions of it in manuscripts. A guest star has appeared in the sky. Chinese astronomers said, oh, a guest star has appeared in the sky, all hail. Well, not quite, but it was this when the Crab Nebula went, when the Crab supernova went off in 1054, it was visible during the day for a month. So even with the sun up and everything, you could still see a bright star in the sky. How are we doing? Good. All right, now let's try and put some sort of, make some sense of this. So remember now, I've put our little picture of our rotating magnetospheric blob, and I've aligned the rotation axis with this jet. Now remember those escaping magnetic field lines? What do you think they're going to look like when they escape? They're going to spiral around. So the magnetic field line, as it comes out from the top here, is going to spiral around, and the magnetic field line from the bottom is going to spiral around. And this coil of magnetic field, you can think of it as a coil of magnetic field, provides like a funnel to fire out this jet of particles, and that's why the jet is there. And I have a better picture later on, but the magnetic field lines that come out sideways, out this way. So if you imagine my magnetic field lines are coming out, but then as I turn, they kind of bend. They kind of bend around like that. And so you're going to end up with like wisps of magnetic fields waving outwards. And so it's this magnetic field that's wisping outwards that drives the particles out and makes them radiate and makes this pulsar wind nebula. Now, I put this up here more for myself than for you guys, just to hammer home that the pulsed emission comes from the magnetosphere region. The emission from the pulsar wind nebula is not pulsed. So even though we saw this movie and you saw kind of wisps of stuff kind of moving or whatever, that is not the pulsar. That is like on much longer time scales. And so we can, for most telescopes, the Crab Nebula is a very, very steady emitter. It doesn't vary. There's some variation that's now seen, but it's on long, long time scales. And now, remember this guy from week 1, the Guitar Nebula, which this is the supernova shockwave here, and I told you that the pulsar lived at the tip here. Well, this glowing kind of wake behind this is the pulsar wind nebula of this pulsar. And so, come on now, there we go. So this is an image again of the, now this pulsar wind nebula has this sort of tail, kind of cometary-like tail, because this neutron star has spin kicked at it, so it has a high velocity. So all the particles that are sort of being leaked out of it are sort of like spilling behind it. And so this is, and you can see, it's not, it would have been better to have made a kind of little movie, but if you just look at this box is at exactly the same place in each frame. And so if you just look at where the tip is with respect to the white line, you'll see it's like further away, closer, and then much closer again. So this thing is, we can actually watch it whiz across the sky. That's how fast it's going in just the space of 20 years or so.
Are they always evolving?
Are they always evolving? So I don't know exactly what you mean by that.
Well, I mean, is it ever just stay for a long time so that you would just see what you saw now a million years previously?
Yeah, I mean, this particular pulsar is an extreme case in that it has a very high K velocity. So whatever evolution associated with hurtling through space, that's happening very obviously in this example. But in other examples, the evolution is not so obvious, and they are considered pretty steady, actually.
But basically, they are like everything else changes all the time.
Yeah.
Basically, they have to be changing.
Yeah. I mean, one of the key things that I told you, or that I hope I told you and I'll remind you of, is that the thing that's powering the emission is the rotation. And this rotation is slowing down. So like the energy that's in the flywheel, the energy that's in the energy source is getting leaked away from it. It is losing energy. So yeah, the power source is dying, but it's dying incredibly slowly for our purposes. It seems pretty constant. How are we doing? Would you believe I've done 72 slides? Wow. Did it feel like that? More than 2 slides a minute? Now, where are we? The next one. All right, here's another guy. This is Vela. You saw, here's again my little cartoon. You see, here you more obviously see the jet coming out the backside here. And in Vela, I almost want to just sit down. Look at it. In Vela, you see very nicely this sort of torus, 2 toruses, one associated with the stuff being spilled out of one pole, and one being associated with the stuff spilled out from the other pole. And then the jet that comes out because of the sort of back end of one pole spiraling around like this. Now, as I say this, one thing I should say is that Pulsar, there are we have 2,500 known radio pulsars. And very, very few of them have nebulas like this. Only the young ones, the really young ones, the Crab Nebula is only 1,000 years old. It's a baby. So only the really young, energetic ones have enough energy to make a nebula like this glow. As pulsars live for a long time, but as they age, this action goes away, and most of the time all you see is what's happening right in the magnetosphere, which is what comes out in the radio emission.
But the nebula still there.
No, the nebula disappears. So for most pulsars, you stare at them, and you don't see anything except the radio beam.
And then you quit?
Do any of them quit? Yeah, we haven't quite seen them quit. Like, we see it on Tuesday and it's there and not there on Wednesday. But yeah, they do tend to fade out after a while. And we might talk about that in a couple of weeks. So I might kind of talk about the details of that transition. Oh yeah, just want to remind you about Vela. That was the one that sounded like a helicopter from week 1. What's coming up? All right. Okay. So we're going to step back inside the magnetosphere now. So what we've done is we've done like the radio beam, and then the magnetosphere, and then the magnetosphere bleeds out and makes a nebula. Now we're going to go back into the magnetosphere and talk about the other emission, the X-ray stuff, and the optical stuff, and the gamma ray stuff. So one of the things which I try to say in the handout, which I've tried to say today, is that the radio beam is coherent, and so it only comes out at the poles where the magnetic field lines are collinear, and so you can get this coherence condition. You don't need that for X-rays and optical and gamma ray stuff. They're incoherent. One electron shooting off an X-ray photon is good enough. We can see that X-ray photon. Radio is so kind of lacking in energy. Radio waves are not very energetic. You need a lot of them coming at you at your telescope to see it, and that's why you need this coherence. You need the coherence in order to get enough radio photons out of the system in order to see it. Whereas if you make an X-ray photon, and we can kind of see that, we can see like very easily. So that's why we don't need coherence for the X-ray and optical stuff. No. So we don't need the coherence argument I said. We don't need any of that. We just have one individual electron radiating one gamma ray or one X-ray photon, and hopefully it escapes and we see it. So the cascade situation that I described that's happening out here, with the positrons that are being accelerated downwards and the electrons that are being accelerated upwards in this cartoon, the guys that move along the magnetic field lines that would now stop being coherent because the neighboring magnetic field line is moving off kind of in a different direction. So, but these guys can make optical and X-ray radiation, but what you would expect in this case is that you'll get a very wide beam. So rather than the little pulse that we see sort of coming out like a pencil or a laser beam coming out, with the X-rays and the optical, we can even get like emission in the opposite direction from the same pole. Like in the same pole of the neutron star, because the positrons are moving backwards, they might emit a photon that will come out this way. So in this cartoon, from the same region, we can have a photon coming out this way and a photon coming out that way. And so you can imagine almost that rather than it being a situation like this, where you have a beam like that, you have a situation where you have two beams here and two beams out here. And so you can see emission from multiple beams because of the flaring out of magnetic field lines and because some particles are moving in one way compared to some particles moving in the other way. And so this is what we see. So this is Vela, the same guy I just showed you. Now on this plot, we're getting close to the end, right? So on this plot, what is plotted here is the phase twice. So the same thing that happens from 0 to 1 happens from 1 to 2. It's just repeated. And can you see the red curve that comes down and then rises again and then falls and rises and falls? That was our helicopter. That's our radio pulse right there. So it happens once per rotation, and in this diagram we put that sort of at 0 and at 1. So this is now the black here is the gamma ray emission. So the gamma ray emission doesn't look like a single pulse. It actually looks like two pulses with a weird, what's called a bridge in between. The bridge in Vela has like a sort of a third fat hump. And it's not aligned with the radio. And so if you look at pulsars, if you see them in optical and you see them in X-rays and you see them in gamma rays, typically you find a pulse shape that's totally different, that might have multiple peaks not associated with the peaks you see in the radio. And that's because it's happening at higher altitudes. Or that's our explanation of it. That it's happening at higher altitudes, and we see, and people like Spitowski and Timolkin, the people who did our videos of the tabletop pulsar and the magnetic field, they spent a lot of time doing numerical codes to try and figure out what the geometries are of the emission, and from that we infer the story I've told you. The crab, which I probably shouldn't tell you because the crab is a known rule breaker. It's very, very young, only 1,000 years old, very energetic. And so even though the crab is most of the time where people find stuff because it's the bright nearby one that everybody looks at, its behavior is totally different from every other pulsar. It's an absolute rule breaker. So here, as you see, the radio is the red again, and the radio in the crab we see a pulse and an interpulse, a second, what we believe to be emission from the other pole, and the emission in the gamma rays again in this case is quite similar. It has the dominant peak in the radio is the dominant peak in the gamma ray, and the subdominant peaks are there. And in the same with Vela, you see that there's sort of, whereas the radio switches off, there's your pulse, it switches off, and there's your other pulse. With the gamma rays, you can see that it rises, falls, but it stays on for a little bit, the bridge, and then rises again and falls. So, I'm kind of finished, but I just want, because I feel like I dumped a load on you today, a load of information, so I just wanted to try and recap the kind of key points. First thing is that thermal radiation comes from hot stuff. vibrational motion of atoms, non-thermal radiation, that for the cases of pulsars, non-thermal radiation comes from accelerated charges. Our tabletop pulsar demonstrates how we can tap the rotating magnetic field to generate an accelerating voltage and drive particles outwards. And because we need coherence for the radio beam, the particles that come out of the pole that manage to bunch together and make the radio beam and make our lighthouse. Particles which escape the magnetosphere because they live on they can kind of get access to open field lines. They can't co-rotate at the speed of light, so they kind of spill out of the magnetosphere. For young pulsars, they fill what's called the Pulsar with Nebula, which has awesome X-ray pictures. And in the Pulsar with Nebula, we kind of get evidence for this story of the magnetic field lines spiraling out and making a jet, for example. And then finally, for the optical X-ray and gamma ray emission, we don't require coherence, so the emission can come from at higher altitudes. And because it comes from higher altitudes, oh yeah, let me say one other thing. And I think I said it in the handout. If you want to, so someone might ask me a question, why does the gamma ray emission not come from the pole? Why does it not come from the pole? Like, why must it come from higher altitudes? Why not lower altitudes? The reason is because at lower altitudes, it's closer to the strongest part of the magnetic field. So if you make a gamma ray down here, it never gets out because it bangs into the magnetic field and makes a pair. So gamma rays are being created all day long in this region. They just never get out. They just seed the cascades. They seed all the stuff that fills the magnetosphere. They never escape. And so by necessity, if you want the gamma ray to escape your magnetosphere, it has to happen at higher altitudes, where the magnetic field lines are curved, where we expect the beams to be wider, and that's in fact exactly what we see. So that's the end, and remind you what's coming up. Thanks again. All right, let's have a few questions. Sir.
Magnets. You got a refrigerator magnet or a ball bearing.
Yeah.
You got the Earth. You got the Sun. You have a neutron star. I've never been clear on the origin of a magnetic field on my refrigerator magnet, having something to do perhaps with charges, but I'm not sure.
Yeah.
I have no idea where it comes from in the neutron star. Could you say something about the similarities or differences?
So I guess I cannot say this week. I mean, I can't tell you. I haven't delved into the sort of the details of where the magnetic field comes from. But you're not the first person to ask me that or ask me a similar question. So what I'll do is I'll find a slot in one of the subsequent weeks, and I'll dedicate like 10 minutes to sort of that particular question. What's going on with the magnetic field? So right now I can't give you what I would consider a satisfactory answer to that. But I'll prepare something in a future week and we'll go to town on it.
Does the coherence you've been talking about here, does that have any relationship to what I've heard called coherent light and laser?
Coherent light in
lasers.
Yeah. I mean, in laser you have a sort of this, you have this inverted states. You have these sort of states that are waiting to be de-excited, and when you de-excite them, they all emit at the same time. So in a sense, you have a situation where all guys go at the same time. The laser mechanism and the coherence mechanism in Pulsar are not the same coherence mechanism, but the concept that you have a group of emitting particles all acting simultaneously together, that's the key idea of coherence. How that coherence arises it can arise in different ways. And yeah, maybe I've told a very, I probably shouldn't say this, but maybe I've kind of convinced you all that this is exactly what's happening. This is exactly what's happening. And actually, and as was probably illustrated for those of you that read the abstract for the series, people really are sketchy on the details. Particularly the radio beam, actually, which and one of the reasons why the radio beam is such a difficult beast to constrain in a way is because the energy that comes out in radio waves is tiny. It's absolutely tiny. I heard somebody analogize. It's like asking what's happening with the radio beam is like asking, or trying to figure out what's happening in the pulsar by looking at the radio beam. It's like trying to figure out what's happening in an internal combustion engine by looking at the drips from the exhaust. like there is just no energy at all. Like the amount of energy that's in this pulsar, most of that energy is converted into the wind of particles in the magnetosphere. That's where the energy budget has gone from. The emission, particularly the radio emission, is tiny. And the optical and X-ray and gamma ray emission is a larger percentage, but overall it's still a small percentage. So your question was?
About lasers.
Well, there you go. I did, yeah. Go ahead.
The Bailiff slide shows those two huge rings with a really big gap in between them. What explains that
The gap.
And I'm sure you know that's maybe not really a false image, but it's orange, and
Yeah.
I'm sure you could take it with other filters.
So two questions. What's with the colors and what's with the gap? So let's start with the colors. Yeah, this is both the orange Vela picture and the blue, or maybe even the orange Hubble picture of Crab. But in any case, the Hubble stuff was optical, and it was probably at one wavelength. I don't know what wavelength it was at, but it's a single wavelength or a small range of wavelengths, optical, but then just for illustrative purposes, colored in as orange. The X-rays from the Crab Nebula and the X-rays from the Vela Pulsar are X-rays, so we have to give them a color when we make a picture, and so that's why it was orange and blue. So they are completely false color images. The reason for the gap, I maybe could have talked a bit more about this, but I did, fill up a whole hour. There's so many places you could go. You could talk about, we could have a whole Compton lecture series on Pulsar, So I'm pretty sure what's happening with the structure of the nebula is the fact that this thing was born in the supernova explosion. And so there was whatever wind of the pulsar, of a massive star. There was like your massive star that we had last week, and all the wind that it blew off over the course of its lifetime. And then there was an explosion, and the shock wave goes out. And so kind of in the vicinity of, and one of the things I didn't talk about last week in the supernovas is there's also kind of reverse shock waves. So when a shock wave comes out from a pulsar, it can or not from a pulsar, from a supernova, it can sort of bang into the wind of the star that was blown out, years earlier. And so after a while, it can actually bang into that and maybe even reflect a bit back. And so you can have these reflection waves too. And so pretty sure the distance between the rings that we saw is to do with where you're dominated by the radiation coming off the wind, and where you're dealing with a collision against something else, something that was previously there. So it's something like that. The second ring is about where you're starting to collide into the interstellar material that was left after the supernova.
I may be anticipating next week's lecture, but you have a massive object rapidly rotating, dragging space-time with it. How can you isolate the effect of that from what we see?
No, this is a fine question. So, I am going to talk much about that actually next week. But, right. So in order for the kind of picture of the magnetosphere with the bending magnetic field and all the rest of that, there are GR, general relativistic effects, in there too, that sort of bend stuff and warp stuff. So there is the bending and warping of space-time happening close to the pulsar, along with all the magnetic field flailing around too. But that is sort of stable in that there is the potential well, and the potential well has certain retarding effects and bending effects. But after all that's happened, you can just sort of say, okay, this is the surface of emission. Like if you sort of draw a line and say, okay, you know, whatever it was that led a photon to be coming out of this direction, behind the fence. Like we put a fence around the pulsar and went, okay, behind the fence, we got a lot of the bending magnetic fields and the potential well and whatever. And so that affects, like a pulsar that comes out this way, after it traverses all that mad stuff, might be coming out in a different direction. But after we put the fence there, we say, okay, something comes out this way. And so you can just sort of wrap all of that up, wrap all that geometrical stuff up, kind of behind the fence. So, you know, the people who really study it need to put in the GR effects and so on, but for the purposes of looking at the pulsar, and looking at the pulses and the pulse separations like the relative distance between the pulsars, the relative distance between the peaks, for example, all of this is happening in the same potential well. It's like clocks are ticking here at whatever speed they're ticking at, and they're ticking at this speed because we're in this potential well. I will talk about this next week. And in a different potential, if we took a clock away, it would tick differently, but you can just consider them, you know, you can just consider all that to be happening, and it doesn't really have to be reflected in what we see, because it's sort of, it's relative, basically. That's it.
It takes energy to make a particle curve in its path.
Yeah.
If a particle is curving in a magnetic field, it's gaining energy from somewhere. Is it subtracting energy from the magnetic field?
It's subtracting it. So the thing that accelerates the particles is the electric field. And the thing that constrains how they move when they're accelerated is the magnetic field. But the electric field is caused by the rotation of the magnetic field. So it's tied in together. The magnetic field is rotating, it makes an electric field. The electric field can accelerate particles. Particles that see charges that are moving in a magnetic field get constrained by how they move. But all the energy at the end of the day is all coming from the fact that you have a magnetic field that's rotating. So it's the actual kinetic energy, in a sense, the actual energy that's stored in the rotation that is being bled off in all this particle creation. The thing that makes the nebula glow, the thing that makes all the particles, that accelerates all the particles, that makes them radiate at the end of the day, is a giant spinning flywheel.
But is a certain amount, does the rotation slow down minimally as a particle is curved due to the field that the spinning particle is creating?
I kind of don't know exactly what you mean.
Well, there's conservation of energy, right?
Yeah.
If the particle is gaining some kind of energy.
So it isn't so much. It isn't gaining energy. I mean, the particle is being accelerated by the field. So it is. I guess you could say it's taking energy from the field, and then it's turning that energy into photons. So it's like I'm a charge, and you're pushing me. And I'm now spending the kind of energy you're giving me by shooting out photons everywhere. So it's like, does that help?
Well, the point I'm trying to make is that the field loses energy when the particle gains energy. Is that correct?
Well, okay. Yeah, you could say it that. You could say that the field loses energy as the particle gains energy, but the field just taps back in. The field is constantly being replenished by the fact that it's got this power source. It's like you're saying a battery. Like if you connect if you turn on a torch, the battery does lose energy to make the light come out of your torch. But if you connect your battery If you instead don't have a battery-operated torch, but you have, you know, electrical cable going in, and you're tapping into some other power source. So even though you're kind of losing energy, you know, you're gaining from, there's still energy coming in from the power source, which is the rotation. And of course, that rotation has to slow down. They all have to slow down in order, because they are spending their energy. So there is conservation of energy, but the electric field could be said to be losing energy, but it just taps into the power source to keep it sort of steady, relatively steady. I mean, like what we talked about, the spasmodic oscillations, the fact that there's sort of actually I should have shown some pictures, because if you look at the pulses, in very high resolution, you actually see that an individual pulse is actually a succession of tiny little pulses, and each one of them is like a little coherent beat, a little coherent zap of that oscillating current that's happening in there. Did I do it?
Yeah.
Happy?
Maybe what we are looking for is a mechanism. Maybe a mechanism that field imparts this energy to power.
It's exactly the same as what's in your TV. It's just the same as what's in your TV. What was in your old television set. It's an electric potential. A potential gets set up a voltage. A voltage is placed down like as if you place down two plates. That voltage is placed down because the magnetic field makes it, because the magnetic field is turned. So it is just like putting a battery down. The battery just happens to be sort of not visible and is there because the magnetic field is moving. But a battery is put there, and a field and a particle that you plop in that electric field is just going to accelerate just like it does in your TV. I mean, it accelerates at much higher velocities, of course, gains a lot more energy, but the mechanism is no different.
You show an angle between the magnetic poles and the axis of rotation. Is that necessary, or is that just accidental?
That is the zoology of the universe. Some are aligned or more aligned than others, some are...
Okay, so there's not a fixed angle?
No. I mean, per pulsar there's a fixed angle. Each pulsar has its own angle.
For that one pulsar?
So the kind of key angles in the problem is, what is the rotation angle? So if we say the rotation angle is this way, what is the dipole angle, and what is the viewer angle? So there's three or two angles or three lines.
But it is possible for them to be aligned. If they were, then you wouldn't see it.
The emission will be different, yeah. I mean, I don't know if it would ever be so perfectly aligned that there wouldn't be a field created and an emission. But yeah, it would look.
There's no relationship between the two that would prevent them from being aligned.
No.
So you made several references to the direction of propagation of the photon. For example, you had opposite directions from positrons and electrons. And it sounded like you were speaking of individual photons. But in quantum mechanics, I'm told that when we talk about probability of detection, it's a spherical propagation of plane waves superposed.
So you asked me this question on day one. I remember Emil was sitting there, and I looked over at him and I go, "Holy crap! How am I going to explain?
He's the guy that told me about the spherical propagation."
Yeah. So the only thing I can tell you is the same thing I told you in the first week. Is that, how do I say it? Feynman himself would say this very staunchly. He would say that quantum mechanics is a tool. It's a tool to help us describe situations. And when we are in a quantum situation where we're talking about very, very small behavior inside the atom, then we take our quantum mechanics wrench out, and we need that to explain what happens. When we step away outside the quantum bubble, outside the quantum, the area where we need the quantum mechanics tools and toolkit, once you step away from that, it relaxes into the classical descriptions. The classical descriptions are valid, absolutely perfectly valid. And if you try to use your toothpick to take apart like something huge, I mean, I can't do it. I can't tell you how to construct, an airplane or a car engine with a toothpick. But if you need a toothpick sometimes to get at the problem, then you take out your toothpick. So we have a spanner, or a forklift truck or something. So we are in the forklift truck regime, and I cannot bring it into the toothpick regime. Just can't. I can't help you understand this problem from the kind of complexities of quantum mechanics, because it's not a problem that's suited. That description is not suited to this problem. Of course, underlying, if you had an army of people out there with toothpicks, they could build you a car probably. But I can't do it. Sorry.
I'm sorry.
How far is Crab? How many light years or parsecs?
It's 2.5 kiloparsecs, I believe.
So it's an hour without galaxy.
All the pulsars we know of, except the handful that we know of in the imaginary clouds, are in our galaxy. All right, got time for 2 more. So you're number 2. Go ahead.
Yes, what is the half-life of a typical millisecond pulsar?
Oh, what is the half-life of a millisecond pulsar? You mean a millisecond pulsar particularly?
Yeah.
Oh, they're going to live the whole universe. They're never going to die. I mean, unless they are unlucky enough to be involved in a collision with another solar system body, they're going to spin for as long as the universe exists. Anyone else going to take the last flight? All right, let's call it then. See you next week.